Hi friends, through this video let us try to understand the physics of semiconductor through VK lectures. Consider an atom here, and the atom's stability is determined by the number of valence electron in its valence shell, which means the number of electron present in the outermost shell. For a stable atom, the number of valence electron must be 8, which means they have completely filled shell. Some examples are helium, neon and argon. They are also called inert gases. Now let us see what happens if the number of valence electron is not equal to 8. For that we have two categories. We can take the number of valence electron to be less than 4 and more than 4. For that, first let us consider an atom with less than 4 valence electron. Some examples are sodium, magnesium and aluminum. They have 1, 2 and 3 valence electron respectively. For example, let us consider an atom with 3 valence electron, and due to electron being negatively charged and the nucleus being positively charged, there is an electrostatic force of attraction between them, which is given by 1 by 4 pi epsilon naught q1 q2 by r square, where this r is the distance between them. Now similarly, you have in the inner shells electrons placed, and due to these electrons the outermost electron will be pushed away. This is electrostatic repulsion. So this electrostatic repulsion is greater than the electrostatic attraction between the electron and the nucleus. So since there is only 3 electrons, they can't fight with this inside electrons, so they will be pushed away. Though they are bound to the nucleus, they are free. So since they are free, they participate in conduction of electricity. That's why this type of materials are called conductors. Some very good examples are silver, gold, iron, copper, etc. These all have less than 4 valence electron in their outermost shell. Coming to the atoms with more than 4 valence electron, here we have phosphorus, sulfur and chlorine with 5, 6 and 7 valence electrons. Since there are more number of valence electron, electrostatic attraction also increases. And also the electrons in the innermost shell, in the inner shells, will have to counter more number of electrons. So due to that reason, attractive force become more dominant. And due to this reason, our size of the atom decreases. As you have learned in your chemistry 12th standard, size of the atom decreases as you go along the period. Your atom size decreases due to the attractive forces becoming more dominant. And here you have to take this point that since it is becoming smaller, size of the atom decreases, the electrons becomes more close to the nucleus and are more bound to it. So this reason prevents them from taking part in conduction. So they do not take part in conduction, and that's why they are called non-conductors. So between the two classes of materials, that is the conductors and non-conductors, we have another group of material called semiconductors. Like between a seater and a sleeper, we have another category called semi-sleeper. Between a conductor and a non-conductor, we have a group called semiconductors. The semiconductor has four valence electron, and examples are silicon and germanium. So an atom with four valence electron. Now, the moment we begin the semiconductor chapter, we begin with silicon and germanium, and we forget the fact that carbon is also coming under the same group. Carbon also has four valence electron. And this is a question for you. Please comment your answers below. Does carbon forms a semiconductor? If yes, why? And if not, why not? Let us consider two semiconductor atom. You can either take silicon or germanium. They are also called pure or intrinsic semiconductor. This is colored in blue, and you have pentavalent atom, examples phosphorus or arsenic, and the electrons number in the valence shell is 5. And we also have trivalent atom, aluminum and gallium are the examples, which have 3 electrons in the valence shell. These colors are uniform throughout our lecture series, so please try to remember. Now let us introduce this pure semiconductor to a pentavalent atom and another pure semiconductor to a trivalent atom. Now what happens? This converts the intrinsic semiconductor to an extrinsic semiconductor. Now this process is called doping. Now let us make this point very clear that the atom we began with, the semiconductor, is electrically neutral, and also the pentavalent atom is also electrically neutral. Here this is also electrically neutral, and the trivalent atom is also electrically neutral. So the byproduct that we have got after doping is also electrically neutral particle. Okay. Now let us see what happens to the semiconductor atom that has been introduced to the pentavalent atom. As stated earlier, atom require 8 electrons. 4 electrons are being contributed by this semiconductor atom, and 5 are being contributed by pentavalent atom. And out of these 9 electrons, the 8 goes for sharing between them, making them completely filled orbits, stable. But where does this one electron go? This just revolves around the molecule. See, this is how it revolves. It will be revolving around this molecule, and since this electron is negatively charged, this type of semiconductor is called n-type semiconductor. And even though there is an extra electron here, our n-type semiconductor is also an electrically neutral. And now here you have another question. What if we dope this pure semiconductor with an atom having 6 electrons in the valence shell? See, instead of 5, if we have 6, what will happen? Please comment your answer below. Now here is a serious problem. The semiconductor atom which is being doped with the trivalent atom has altogether 7 electrons in its shells for sharing. but we require one more electron, and in that place of one more electron we just have a void space. And now this void space is being converted to a hole and an electron. That is, from this void space we are drawing out electron which is negatively charged. When we are drawing it from a space, it becomes a hole which is positive charged. Now that means we are converting this void space into an electron and a hole pair. Now you see here our problem is solved. We have 7 plus 1 electron hole pair, that is together of 8 electrons and 1 hole. This is similar to that of the previous case. Instead of electron revolving around it, we have the hole, and since this hole is positively charged and it is revolving or moving around this molecule, we call it p-type semiconductor. Now just like the previous question, you can ask yourself, what happens when pure semiconductor is doped with divalent atom instead of trivalent atom? If you have one more void space here, what will happen? We have here two regions. Both are pure semiconductor materials on the region 1 and region 2. Now the first region, what we are going to do is we are going to dope it with trivalent atom. Once we drop it with trivalent atom, you have a hole in the molecule. And in the region 2, we are going to dope it with a pentavalent atom, and there you get an electron in the molecule. Now what we are going to do is we are going to bring them close. This is what happens when you bring two regions close together. Here you have this region which is called P region, because these regions all are having holes, and here you have N region, and when you combine them together you get something called PN junction or diode. This junction is called PN junction, or the material as a whole is called PN junction diode. Now here let us very closely watch what happens at the junction. This is N region, and here you have P region, because it is full of holes. You have P here, and this is electrons here, you have N region here. The electrons in the N region has affinity towards P in the hole region, and the moment it is being combined, the electrons from this N region will combine with the holes in the P region. So in this process, leaving of electron from the N region creates a positive charge at the N region, and similarly this entry of this electron creates a negative charge in the P region. Now we can see two equal and opposite charges separated by some distance, which is nothing but a dipole. At the positive point here you have positive potential, and this negative region you have negative potential. And as the potential decreases from this positive end to this end, your electric field is given by E is equal to minus del V. Now the direction of electric field is in this direction. Thus an electric field is developed between this region. Now this electron and hole pair will continue until there is a sufficient potential difference developed across its junction. Now this potential which is developed is called barrier potential. This barrier potential will prevent the further movement of electron through this junction. The moment this electron reaches at this point, the negative potential from here will be opposing the electron from entering, while this positive charge here will be taking or pulling it towards it. The region where this barrier potential is developed is called depletion region, and for silicon you have 0.7 volt as the barrier potential, and for germanium it is 0.3 volt. The biasing of potential and its characteristics will be discussed in the next VK lectures. Let us know about this video through your likes, comments and dislikes. Here we are presenting our Telegram channel where you can get the notes, videos, daily questions and weekly exams on the topics of physics. Thank you.